Assalamu alaikum. My name is Tahmid Fardin Fahim, student ID 2100212320. So today I will be demonstrating the working and construction of SAP, and my group's name is Virus. My other group members ID is 2100213553, 2100213092100021 2100213007, 2100213492100021 21002353. To actually run our SAP, we have some opcodes from our manual. So we know that load is 000, add is 001, subtract is 010, and output is 011, and halt is 111. To run this computer, we first have to give the proper instruction data in the particular RAM address. So let's say we can say that the RAM will take whatever the value that is stored in the 7th position of our RAM, which is 110 address location of our RAM, and it will store that value, that particular value, in our accumulator. And again, we will take whatever the value that is stored in the 8th position in our RAM, and they will add them, and we want to display them out. So for this particular location, we have to give the associated instructions in our RAM. So to give inputs, we have to make the r/p pin to 1, and we know r/p is run/programming. So if run/programming is 1, that means the address selector is taking inputs from our input unit, and when is r/p is 0, then the address selector is taking input from the memory address register. And also, if we want to write some values in our RAM, we want to make the r/w or read write button to 0, and if we want to extract that data out, we have to make the r/w to 1. All right, so in order to save those data, we will first use first three of the RAM location, let's say 000, 010, and 011. These first three locations as the instruction of what we are doing. So in our RAM we have total 6 inputs, so we will divide them, and the first three will actually indicate what instructions we have to follow, and this second third 3 bit will determine from where we need to extract our values. So let's say for the first instruction we will be saying that we have to load whatever the value that is stored in our RAM location 7. So we have to then first give our RAM location is 000, and we will be storing 000 and 110. So the first 3000 is actually indicating our opcode for load, and the second 110 is saying that load the data which is stored in the RAM position 7. And then again we have to change our address location to 001, 010, and we have to give input is 001 and 111. The first 001 is actually indicating our add, it is the opcode for our add operation. So, and the last 111 is actually indicating our 8th position in our RAM. So it is saying that we have first saved whatever the value that was stored in 7th location, and now we are saying that we have to add whatever the value that is stored in our 8th position, and then we have to store them out. We have to store them, and for our output operation, we then have to use our third memory location. So the third memory location, we have to give address, it is 010, and the value we will be storing is 011 and 000. The first 011 is actually saying that output the value that was stored previously, that what we have calculated, want to see that output. And the last 000 has no significant values, so we can give any values we want. So as we have already previously said that we have to load what's stored in 7th position, and we have to add that number with what's stored in the 8th position. So then next step, we have to give inputs in our 7th and 8th location of our RAM. So we will do the same thing, and we will give inputs in our 7th and 8th location. And then for the computer to run itself, we have to make the r/p to 0. That means it will now then select the values from the memory address register, and r/w to 1, so that it will be taking the values. We can extract the values, and we can do all these phases, all these in between phases with the help of our controller sequence. The controller sequence should be doing all of that by itself, but for some reasons our controller sequence doesn't behave like that. So what instructions we have already said that should have been done by the instruction register automatically, we can give the same input manually. So we can say that let's first let's Alright, so we will be now giving this instruction manually. So let's say we are saying that we need to insert some values in the RAM location 000, and then we have to store that particular value in our accumulator, and then we will be again giving some information in our RAM location 001, and we want these values to be stored in our uh, B register. So in order to do that, we have to make the r slash b to 1 and r slash w to 0. So if let's say we are giving 000 values in our input unit, and the values will be 111 0 So this 111000 is now saved in our RAM. So if we want to see that value in our bus line, so we have to first give the arrow pin to 1 and the r slash w to 1 as well. So we should be seeing that 111000 in our bus line. Alright, so now we have to save that particular value in our accumulator. So to do that, we have to give the our value AI 1. So we should be seeing that 11100 value which is saved in the accumulator. Right, so now we don't want to save anything else values in our accumulator. So the accumulator AI is 0 and our arrow is also 0. So accumulator has saved the value 111000. So let's say we are giving another set of information in our location 001. So to do that, our r slash w to be 0 again, and the address will be 001. So we are giving another value 110000, which is 48 in decimal, and the previous one was 56 in decimal. So let's say we have already stored that value in our RAM. So if one want to display that value in our bus line, we have to give the arrow to 1, and also this r slash w to 1 as well. So we should be seeing that value in our bus line, which is yes 0110000. So now we want to save that value to our B register. So B register will be 1 as well. So we should be seeing that value. Here it is. We have saved this value 110000 in our B register. So now we don't want to save any other values in our B register. So B register will be 0 and R goes be 0. So we have successfully saved both the information in our A register and B register. So let's say we want to subtract them. So we know to subtract them, we have to give the SU button to 1. So now they will be subtracted. So we can also see that value. So that we have to first give the EO button to 0. So it will be displaying the calculated subtracted result in our bus line. So we can see this value is 00100. So we know this is 8 in decimal. So it is kind of obvious that we are subtracting 56 minus 48, which is 8. So we can also see that value in our 7 segment hex display. So yes, it is 0008. So we can do the same operation that we want to see if we, let's say we are subtracting 48 minus 56, the value will still be 08, and this part will be 1, as it will be indicating that we have minus 08 value. So we can do the same thing here. To address one of our improvements, this is my design of ALU or arithmetic logical unit. So I introduce the external sign bit operation, so we can also see whether in a subtraction operation whether it is a positive number or negative number. So in order to see that, if I have to go it through, uh, here we just used, first of all we used normal 4-bit parallel adder, and then we used 6 of them, so it can add 6 numbers, and we are feeding the values of the accumulator directly, and we are feeding the values of B register that goes through an XOR. So we know XOR behaves like a buffer circuit when the other end is 0. So for a normal addition operation, this whole line will be 0, and for subtraction operation, this whole line will be 1. So this XOR gates will act like an inverter, so it will invert the values of the of the B register, and then it will add them. So we can see the answer, but there is a problem when the value of A is less than B. So when A is greater than B, then we just simply we just simply ignore the n carry, and we take the values of which is left in the other 6 bits. But in the case when B is greater than A, when we don't have any n carry, we then have to give we have to go through a further operation, which we have to then in the arts complement it again, and then we can have the final answer. To do that, I introduced again 6 bit parallel or adder, and I introduced 6 XOR gates for the 6 inputs. So this NOT gate will actually determine whether we have any n carries or not. So it is going we know when it is going through all of the XOR gates, it's one leg. So when we do have an n carry, that means we don't need to reverse it. That means this one will be that n carry will get inverse to 0, and all of these XOR gates will act like a buffer. But when we do not have an n carry, this 0 will invert that 0 to 1, and this XOR gates will inverse the result, and then we have to add 1. So we have 6-bit parallel adder. So the first 6 bits are coming through the results of the previous results, and we need to add 1 when we do not have an n carry. So this inverter will feed through this B0, so which means we are adding a 1 only when we do not have an n carry, and we are also reversing it, so we can get the perfect result even when A is less than B. So I used 6. Alright, to demonstrate one of the examples, let's say we are subtracting 56 minus 48. So this means 56 means 1 1 1 0 0 0, that means 56, and 1 1 0 0 0, that means 48. So the answer should be positive 0 8. So we should be seeing 0 as the sign button should be 0, and then we will have 0 0 1 0 0 0. So if I have to see, if I just click this on, and let's say this will be on, and this, as we are subtracting, yeah, so it will be 0 0 1 0 0 0, that means it is 8, and this 0 is actually saying that we have positive 8. So if I have to reverse this thing, let me say we are reversing, that means we are subtracting 48 minus 56, so we should be getting minus 0 0 8. So yeah, exactly the same thing, 0 0 1 0 0 0, and this first sign bit is 1, that means it is indicating that we are having minus 0 8. So another improvement, that we used our binary output and we converted into decimal output. So we have done that by converting that corresponding binary into BCD output, and then we use the 7-segment H display to display them out. So we have done that by method called shift at 3 register, or double method. In this method we actually shift the MSB to one side left. So we do that, and in every time we analyze that the number that is in the box is bigger or equal than the value of 5. So if it is less than 5, then we keep doing our shifting, but when it's greater or equal than 5, then we add 6 with the number. So we have done that by we constructed truth table, and we plotted the corresponding Carnot map in this. So if we have to go to the child sheet of each of this section, then this is the child sheet. We have used a combinational logic that it will analyze that if the number is less than 5 or not. If it is, then it will pass, and if it is not, I mean, it will shift, and if it is not, it will add 6 and then it will pass. So we use 3 of them, and if we want to demonstrate that, let's say we are now it's 0 0, so this means 0 0 1, and this means 0 0 3, and then this is 2, this will be 6, 14, 30, and we can maximally display 63 here. So yeah.